Okay, so this is going to be our last sections in Unit 3 for this portion of our unit here. We're going to go back over representations of solutions. Should be review. Went over a lot of that, hit a lot of that in Unit 4. But for this particular section, we're going to go over chromatography and distillation because both of those are based off of intermolecular forces or interparticle forces. So that kind of falls in with what we've been talking about, the IMS. So the current problem set is over 3.1, 3.3, 3.8, and 3.9. Those are what you're going to see in the current problem set that's due next week. Okay? So let's look here at our learning targets. Interactions between intermolecular forces influence solubility and separations of mixtures. So using particulate model diagrams for mixtures, represent interactions between components, represent concentrations of components, explain the processes of chromatography. There's 3 types: paper, thin layer, and column. And discuss the components of how the components interact with the mobile and stationary phases based off of intermolecular attractions. That's all part of chromatography, the mobile and stationary phase. And explain how distillation separates components of a solution through the IMFs with regards to vapor pressures and boiling points. Okay, so kind of a review, going over particle diagrams again. This one goes into the idea of dissolution of an ionic solid. As you can see, we have sodium bromide crystals and we have water molecules. They give you a key of how to draw them. The structures are represented to the left. This is literally an FRQ question I pulled out of an old exam. Okay, so pretty much worded down to the T exactly like it would be. Okay. In the space provided, show the interactions of the components of sodium bromide, AQ, by making a drawing that represents different particles present in the solution. Base the particles in your drawing on the particles shown in the representations above. Include only 1 formula unit of sodium bromide and no more than 10 molecules of water. Your drawing must include the following details: identity of the ions, that means the symbol and charge, and the arrangement and proper orientation of the particles in the solution. So if sodium bromide is dissolving in water and we only want 1 formula unit, what am I going to draw? Going to draw which one up here in our lattice crystal is going to represent sodium? The littler one, the smaller one, the white one. Okay, so I'm going to make that one a little bit smaller, and I'm going to put Na and the plus in there because it says I need to identify the symbol and the charge. Now the other one is gray, which I can't represent very well on the smart board, but I'm going to make it a little bit bigger here. The larger one's going to be bromide. Okay. Remember, bromine has the 4th energy level, has 1 more shield in there or whatever to make it larger. Also has more electrons than sodium. But also do remember that Na+, when it becomes the ion, it has lost an electron. So technically, Na+ really only has 2 energy levels, because the 1 valence electron was in the 3rd energy level that has now been given away to bromine to make bromide. So technically, sodium ion only has 2 energy levels, whereas the bromide is going to have 4. That's why you see the differences in sizes. So we would put our Br minus in here. Now, to show its dissolution with water, what are we going to draw here in terms of around our sodium for the water? Oxygen should face inward, and so you draw it like this with the little Mickey Mouse ears, whatever, and like I said, artistically challenged here. Now it said no more than 10 molecules. I like to put 1 on each side, like so, showing that the oxygen is facing inward. Remember, the oxygen has the partial negative charge, so it's going to attract to the sodium, which is the cation, full positive charge. And then around the bromide is going to be the opposite, right? Where we have the hydrogens facing inward, because those are the partial positive side. Oops, that one was a little close. I'm gonna erase that. So I can leave some space to put my hydrogens in. And I put one on each side, but they do not want you to put more than 10 in there because they don't want you drawing all day. So stick to the parameters of what it says, and usually it does give you a count of, or at least a range to stay within. Okay? So there's that, as you can see. All right, so this is one about like the concentration, and you saw some of that actually in the Unit 4 test 2, counting particles and things like that. This could be another one that they give you in multiple choice format. Equal volumes of solutions in 2 different vessels are represented, actually to the right there. The solution represented in vessel 1 is sodium chloride. So this is sodium chloride. The one in vessel 2, we don't know, okay? But we're trying to figure out what it could be. All right, any suggestions where to begin? What should we do here? Count. Counting is always good. So we have 1, 2, 3, 4. The black circles represent positive ions, so that means I have 4 sodiums, okay? All right, so we counted our positives, the negatives here, which are the white circles. 1, 2, 3, 4. So we have 4 of the chlorides. So 4 sodiums and 4 chlorides in vessel 1. Now, we look over at vessel 2. So that's a 1-to-1 ratio, basically. 4 to 4 is 1 to 1, right? A 1-to-1 ratio going on here. We compare over here. We count the positives. What are our positives going to be? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 positives. How many negatives do we have? 16, right? So what kind of ratio is that? 1 to 2, right? So we should be able to eliminate 2 answers offhand right there. Because in the formula unit, it has to be what? 1 to 2, right? So we get rid of A and B. Get rid of A and B. Because KBR is just 1 to 1, so that would not be able to produce a ratio of 1 to 2. Now we have to think about the differences in these. We have the same molarity versus twice the molarity. So go ahead and take a look at that. So copper to chloride here with the same molarity or with twice the molarity? What do you think? Twice, right? Because if this is 4 to 4 and sodium chloride is 1 to 1 in there, the whatever is the 1 over here, the copper, okay, would be a 4 if they were the same molarity, but instead it's an 8, so we know that it's double. So therefore, D is the correct answer. All right, last but not least, another lovely particle model here where we're counting. All right, student mixes dilute silver nitrate with excess sodium chloride to form silver chloride as represented by the net ionic equation below. Which diagram best represents the ions that are present in significant concentrations in the solution, and explain. Okay. So, couple of key context words up here. I'm going to point out to you. Dilute versus excess. That should tell you something right there. The dilute one, okay, out of your silver nitrate here and your sodium chloride, we only have 2 ions participating in the reaction. What are the 2 ions participating in the reaction? Ag and Cl. That means the nitrate and the sodium are spectators, okay? So the concentrations of the sodium and the nitrate aren't going to change because they don't react to many things. So whatever they were originally is what they're going to be at the end as well, because they're not doing anything different. However, the silver and the chloride are going to combine and form precipitate, fall to the bottom, based off of solubility rules and all that, although it tells you that's what precipitates here too. So, out of your silver and your chloride, which one should run out? Based on the context clues that they give us. Silver should run out. Silver should run out because it says dilute. What does it say about the chloride? It says it's in excess. So should you see silver in anything up here? No. So guess what? That means I can cross off that one and that one, right? Silver should not be present in any significant amount since it was dilute to begin with. That means it's limiting. That means it would not be there afterwards, right? So, out of the other two though, should be pretty obvious to you which one we should select. C. The difference between A and C is that there's no chloride in A. And we know it's in excess, so there still should be some chloride present afterwards because not all of it was consumed or used. So your correct answer here should be C. And if you notice too the way they represented the sodium and the nitrate, you can see that since the nitrate was dilute, there's only a couple of those. And since the sodium was in excess, they have 4, which is double that. So they put more sodiums in there than they did the nitrates. Also kind of helps you out there a little bit. All right, so Ag ions limiting, they run out. Okay, chloride ions in excess. Sodium and nitrate are spectators, so they shouldn't be doing anything. So what they are to begin with should be what they are at the end and should still be present in the solution as ions. Wonderful. Now we can talk about chromatography. And this is what your new pivot lab, the thin layer chromatography, is going to be on and measuring. And honestly, I can tell you right now that I wouldn't be able to set that up in our lab as good as it is in the videos. It's really like kind of like the one with the stretching to the surface tension one. I wouldn't be able to set that up as well as it is in the videos. So this is a good lab, good way to practice chromatography. All right, so chromatography, there's paper, thin layer, and column chromatography. They separate them by taking advantage of the different strengths of the intermolecular attractions or interactions. For most things, that's going to be intermolecular forces, but in some cases where we're talking about intra stuff, okay, might be looking at that as well. So, you have the mobile phase or mobile phase. That's the one that moves. You also have a stationary phase, obviously, that remains stationary and doesn't move, okay? Stationary phase is either a solid or a liquid supported by a solid, okay? So really stationary phase, gonna see that it's mostly gonna be solids, and then in some cases, the liquid used is supported and it's like attached to a solid component. Now, as you can see are the paper pictures. They're showing you the separation of dyes, and that's one that it's used for, and that's one we did in Chem 1, where it separated the pen dyes into different, how far they traveled up the paper based off of how attracted they are to the solvent. And the one that travels farther is going to be more attracted to the solvent than it is to the paper. The one that doesn't travel as far is probably more attracted to the paper than it is to the solvent. And that's all based off of those forces interacting with one another. Okay? All right, so paper chromatography, stationary phase is a cellulose paper. That's what our filter paper is made of, is that cellulose material. That's what we used last year in Chem 1 for the paper chromatography. And the mobile phase is a solvent. And so last year, I believe we used acetone, I think, or Could have used hexane. You can use water. Water, although, is also very polar, so using the cellulose paper with water, okay, but two very polar substances. The reason why we know that the cellulose is polar is it has lots of these hydroxyl groups on it, those OH groups attached all around. I don't know if you remember from biology, but cellulose is one of the main carbohydrate components that's found in cell walls of plants, amongst other things. And organic molecules usually gonna have functional groups off it, and the cellulose one has a ton of the OH groups. So that gives it a lot of polarity and the ability, of course, to do hydrogen bonding, because those OH groups allow for hydrogen bonding. Yes?
Water isn't considered to have an OH group, right? Or does it?
Well, technically, I guess you would say it has two.
Okay.
Because the O goes to two H's, and that gives a huge electronegativity difference. But it is not attached to any like carbon chain or anything else, which the organic functional group ones are going to be attached to some kind of carbon chain.
Okay.
Okay? Cellulose is a polysaccharide, so it's a big carbohydrate with lots of hydroxyl groups around it.
Mm-hmm.
All right. The molecules have a greater affinity for the paper or for the solvent. So that's the idea. Which one is it more attracted to? If the molecule is attracted to the solvent, it will travel up with the solvent, go up the paper. If the solute has a low attraction to the solvent, it will come out of solution, be deposited onto the paper, the stationary phase. So be more attracted to the paper, basically. The relative attraction that each component of the solution has, one for the mobile phase, will allow you to separate them, the solutes in the mixture. So, you know, one that's more attractive travels farther, one that's not as attractive, not going to travel as far, and so forth. Now, a couple of things, and they'll have you do this in the lab as well, is calculate something called the retention factor. Right here, I believe I put the picture in there on your notes for you. But the formula is the distance traveled by the component divided by the distance traveled by the solvent. So you have to pay attention to how far the solvent travels to measure that. Now, a couple little things before we call it a day here is if you have a nice centralized small dot, you just go to the center of it, and that's where you would measure the component deal. But if your dot is more like a blob, you could go to the center of the blob and measure it that way, or you could do the top end and the bottom end of the blob and then average those two numbers together. But if it's really like a huge, you know, like oval shaped, you want to go to the middle of it, and that's where you would take your measurement for that particular component. This is very simple math, and you'll be comparing some retention factors in the Pivot Lab, and you'll be looking at a bunch of different organic substances and solvents that have used different solvents, different organic substances. But at least now, since you've seen this, you can start looking at the lab. We will finish these, of course, next time.